Hello! In this how-to video, you will learn what is required to expand a 7SJ85 feeder protection relay with PQ Basic and why voltage variations are so dangerous. The video guides you afterwards through the parametrization to detect, count, and visualize voltage dips. The last chapter will give you an example for displaying the details about the detected voltage dip. In this example, the SIPROTEC 7SJ85 overcurrent protection has been designed specifically for the protection of feeders and lines. With its modular structure, the SIPROTEC 7SJ85 device offers future-oriented solutions for protection, control, automation, monitoring, and power quality. Basic. To expand a new or already installed 7SJ85 with PQ Basic functionality, no changes are on the installed hardware necessary. In our example, the PQ Basic subfunction voltage variation requires 30 function points per voltage current measuring point. Before we start the parametrization, let us investigate the cause of voltage variations and the possible results on consumer side. Voltage deviations. Voltage deviations result from switching operations in the power grid or starting up heavy loads. As a result of voltage deviations, efficiencies of an electrical system may be reduced, or it may be shut down due to an under-voltage trip. In DIGSI 5, you can see we just added a 7SJ85 relay. The 30 functions points allows us to equip the measuring point voltage current 3-phase with the function block voltage variations from the global DIGSI 5 library. Let us expand the settings menu in the function group voltage current 3-phase 1. From the libraries window, we drag and drop the power quality basic function voltage variation into the function group voltage current 3-phase 1. A double click on the function opens the parameters for dip, swell, and interruption. The parameter mode needs to be changed for all three variation types from off to on. The threshold limits are predefined by 90% for dip, 110% corresponding to swell, and 5% is the threshold for interruption. In the section General, we must check the correctness of the predefined value for rated voltage because this value is the base to classify the threshold values of dip, swell, and interruption. The next task is to route the evaluation results into user log and fault record. Expand in the information routing table the signals of all three vent types. A mandatory indication is the warning. Let us route it to a base module LED and into the user log U1. Some more interesting evaluation results are the duration of the event and the residual voltage during the event. For statistical information, we route the dip event counter into the user log finally. The routing for voltage swell and interruption needs to be done accordingly. To get a fault record done when a warning is indicated, we need to design an easy CFC chart. Therefore, we click on Add New CFC Chart. Give the chart a useful name. From the library, we will take an OR element because this element covers per default only 2 inputs. One more needs to be enabled. Now, we connect the warning input signal to X1, 2, and 3. The output Y of the OR element will be attached to the external start SPS of the internal fault recorder. Let us now create a display page to visualize the amount of registered event of type dip, swell, and interruption. The new page appears after double-click on Add New Display Page. Rename the page first, in our example voltage variation counter. Now, we drag and drop the counter signal from each type of event into the display area. Let us position the labels and counter variables on the screen and change the default label from counter to the dedicated event type. Voltage dip, voltage swell, and voltage interruption. Finally, we do some corrections on the layout. Alright, that's it. We will now test the parametrization. Therefore, we switch to the SIPROTEC Digital Twin. Here we can see now our just parametrized feeder protection 7SJ85 relay running in the SIPROTEC Digital Twin. On the front panel, the LED 7, 8, and 9 indicate warnings for detected dips, swells, and interruptions. Let us switch to our new created voltage variation counter display page. There have been already 4 voltage dips registered, and the LED shows us that there is no warning active just now. To simulate a voltage dip on the measurement input, I'll decrease the measured voltage below 90% of nominal voltage. The active warning for dip indicates the LED directly afterwards. The voltage dip counter will be increased from 4 to 5 registered dips. Once more with focus on LED and dip counter. The LED informs us about an active warning signal, and as soon as the event is over, the dip counter will be increased from 5 to 6. To get more details about the voltage dip, we can take a look into the user log on the device homepage. The marked row shows the exact time stamp when the dip was detected. In the chronological next row, the residual voltage is displayed, in our case 64.08% of rated voltage. The voltage dip had a duration of exactly 2.72 seconds. The next log entry is the warning off and the event counter, corresponding to the number we have seen on the device display, the 6th. The fault recorder, which was initiated by our CFC logic, shows the exact trigger timestamp for the threshold of 90%. In our example, RMS drops below 207 volt. The end of the event is marked with the blue cursor on the right side. Here we can read, like in the log entry just before, an event duration of 2.72 seconds. Thank you for watching.